Welcome to video 2 for the mechanical power transmission. We're going to start this video by taking a look at these 4 gears and asking ourselves which of these gears will mesh together. So looking at them, we can notice a couple things, maybe the height of the teeth, the spacing between the teeth. And looking at these, hopefully you can recognize that this gear and this gear are the only two that will mesh. In fact, these middle two won't even mesh with themselves. So when we look at the requirements for mesh, the requirements are that both gears need to have the same size teeth. And what I mean by that is that all the gears, if we were to take a look at how a gear kind of looks, kind of comes down like this, kind of bowed out a little bit. We want to make sure they have the same width. That's what I mean by the same size. And then there needs to be the same spacing between the teeth. So those are the two requirements for gears to mesh. Now the number of teeth is proportional to the diameter. And we call that diameter the diameter pitch. So that's like a constant proportionality, if you will. So the VEX system uses 24 diameter pitch. So what that means then is if we were to measure the diameter of these gears, and by diameter it's kind of tricky to figure out what to use for the diameter. It's not quite at the bottom of the teeth, it's not quite at the top of the teeth, it's kind of in between, kind of in the middle of the teeth. That's where we measure the diameter. And the smallest VEX gear is a 12 tooth. I've got a 12 tooth, 36 tooth, 60 tooth, and 84 tooth. And the smallest is a ½ inch. That's the diameter or pitch diameter for it. So if I were to take 24 times 1/2 of an inch, that equals 12. So that's what that 24 diameter pitch means. If I were to take the diameter of the gear, multiply by 24, that gives me how many teeth the gear has. The 36 tooth has a pitch diameter of 1.5 inch. .5. So basically, going back to this idea then of proportionality, the number of teeth is proportional to the pitch diameter. So whenever you see something that's proportional, that means that it equals some constant times that other. And that constant then is the diameter pitch. All right. So then, let's think of an example here. Let's say that we're using a 3D printer, and what we want is a gear that has 96 teeth. 84 is not big enough. What diameter should that gear have? Well, if I took 96 and divided it, remember that the number of teeth is equal to that constant times the pitch diameter. If I took the number of teeth divided by our constant, that would give me my new pitch diameter. So using that, the number of teeth is 96 teeth. The constant, well, for the VEX system is 24 diameter pitch. We find that we'd have to have a 4-inch gear. Now that we've talked about gears, we can start talking about gear ratios. When we start putting gears together to find out um, how they can be used. So gears, we can use them to transfer power. So if your motor is situated in a position that's farther away from where your wheels are, you can use it to transfer the power over a distance. But they're not used just for that. You can also use gears to adjust the mechanical advantage. So let's think of a bicycle. In a bicycle, you are the motor, and you have limited power. So you want to make sure that whatever power you have is harnessed as much as possible at all times. So if you're going downhill, your load is low. There's very little external torque being placed on you, the motor. So what you would want to do is use a gear ratio that would increase your speed, but have a low output of torque, because if the load's low, you don't have to supply as much torque. Remember, motors are reaction devices. When you request torque from them, they provide it until they fail. Same thing for you. If there's no load placed on you, you operate with no torque. But once someone asks, or once you're put in a position where you're asked to provide more torque, then you do, until you can't provide it anymore. So going downhill, you would have a high mechanical advantage, or, well, a very low mechanical advantage, I should say, to increase your speed. Going uphill, now the load is high, so you'd want to use a gear ratio that would increase your torque. But remember, as torque increases, speed decreases. So that's one reason why you slow down as you go up a hill. So bicycles use gearing to help us do that. So before we start talking about some of the math with that, we need to establish what exactly is mechanical advantage. What does it mean? How can we use it? So mechanical advantage is something that can change the speed of motion, and it can also change the direction that you're doing things. So if we go back to the definition of power, power is the rate at which work is done. If the amount of work increases, the speed at which it gets done decreases. So that's kind of another thing that machines can help us do. So believe it or not, a gear can be thought of as like a simple seesaw. So in this seesaw, we have a fulcrum, which we've kind of placed closer to one end. So we got 2 meters on one side of the fulcrum, 8 meters on the other side. And we want to calculate the mechanical advantage of this system. So first thing you have to realize is that a machine does not decrease how much work you do. So the amount of work you put into the machine equals the amount of work you get out of the machine. And I'll show you that using some math here in a few minutes. So work is a force times a distance. So here, the force for the input, we can think of our force like this. And our distance then would be 1 meter. When we press down on that lever, the output force is on the other side, and we get another distance, an output distance. So over here we have our input distance. We can see that the force and the distance are parallel, which is good because that gives us our work. So work is defined as a force that's parallel to a distance. So the amount of work we put in would be the input force times the input distance, and that would equal the output force times the output distance. And I can do a little rearranging, but before I do that, the definition to mechanical advantage is equal to the output force divided by the input force. So that's an important formula right there. That's our mechanical advantage. So notice, going back to my work equations, I can do a little bit of math, and I can see that the input distance divided by the output distance equals the output force divided by the input force. Well, that right there is mechanical advantage. So I see that mechanical advantage is output force divided by input force, or mechanical advantage can equal the input distance divided by the output distance. So we can go ahead and calculate the mechanical advantage of this system right here. So looking at this, mechanical advantage equals the input distance divided by the output distance. So what I have is 1 meter divided by 4 meters. And I get a mechanical advantage of 0.25. That is unitless because it's a ratio. The meters cancel out. So what does this mean to have a mechanical advantage that is less than 1? Well, remember that mechanical advantage equals the output force divided by the input force. So, doing a little bit of math, if I put that under 1 and or over 1 and cross multiply, the output force equals mechanical advantage times the input force. So let's say this input force was, think of something pretty simple. Go with 4. So let's say the input force was 4 newtons. The output force would be 0.25 times 4 newtons. So if you think about it, 0.25 is the same thing as 1/4. 1/4 times 4, I get 1 newton. So if the mechanical advantage is something that is less than 1, like that, the output force is decreased. We have a lower amount of output force. If the mechanical advantage is 1, then the output force and the input force would be the same number. If the mechanical advantage is greater than 1, then the output force is larger than the input force. So that's all very helpful when it comes to, figuring out what exactly mechanical advantage is. But that's not all. Remember that forces are linear things. We have a rotational version of force, which we call torque. So I can rewrite my mechanical advantage equation to say torque in terms of torque. So I would have the output torque divided by the input torque. So it's the same thing as force. So if I have something that has a mechanical advantage of less than 1, then that means that I am losing torque. So that's like a bicycle going downhill. If I have a mechanical advantage that is greater than 1, then I am increasing the torque. So that's trying to climb up a hill. All right, let's assume that it takes 1 second for you to push this side of the lever down. That means it would take 1 second for the other side to go up. The time on both sides would be the same. So the interesting thing then is that these distances are over the same time. So if it takes 1 second for the input to move the 1 meter, it's going to take 1 second for the output to move 4 meters. That means the output is moving faster than the input by that same ratio of mechanical advantage. So speed is distance divided by time. So I would have an input speed, which would be 1 meter divided by 1 second, so 1 meter per second. I would have an output speed, which would be 4 meters divided by 1 second, or 4 meters per second. So notice what that means then is that the output speed equals the input speed divided by mechanical advantage. And that's important. Now we can also do the same thing for rotational stuff. The rotational speed would equal the rotational input speed divided by mechanical advantage. So if we do a little bit of math here, the input speed was 1 meter. 1 divided by 0.25 equals 4. So that all works out. All right. Going back to the torque, just one more time here. If we apply a force that tries to pivot something, we get torque. So torque is defined as a force that is parallel to a lever arm distance. So going through our math then, the input torque, and this is kind of the same setup that we had before, the input torque was, force times lever arm distance. So for this case, it's 4 newtons times 2 meters, which equals 8 newton meters. And then for mechanical advantage, another way of looking at this, I can, instead of using like the distances it goes down or up, I can use the lengths of lever arms. So I can say the input lever arm divided by the output lever arm. So that would be 2 meters divided by 8 meters, which equals 0.25. So it gives us kind of the same values as well. And then remember that the output torque equals mechanical advantage times the input torque. So I'd have 0.25 times 8 newton meters, and that gives me 2 newton meters of output torque. So again, when the mechanical advantage is less than 1, we lose torque, but we pick up speed. When the mechanical advantage is greater than 1, we lose speed, but we pick up torque. That will conclude video 2.